Hello class. In the previous sessions, we started the topic of solving first order ODEs using numerical methods. In this session, we're going to continue that and introduce the more general form of Runge-Kutta method. Just to give you a summary of the previous sessions and an overview of this session, I created this slide. So we are solving a first order ODE of this form with an initial condition of y at x0 is equal to y0. And if you remember, I mentioned that there is a large family of methods called Runge-Kutta methods. We started with the first order Runge-Kutta, which is also known as Euler's method, and then we introduced modified versions of Euler's method, namely Heun's and midpoint methods, which are second order. And in this session, I'm going to introduce you the general form of Runge-Kutta method that can be extended to third order, fourth order, and so on and so forth. Okay, before I start with the general form of Runge-Kutta method, I thought it's best if we have a refresher on Heun's method, and then with that we kind of build the foundation to go and extend the formula to the general form of Runge-Kutta method. And I've already explained the Heun's method in the previous lectures. So in here I will just quickly give you a summary of the Heun's method. So the problem description is to solve an ODE of the form of dy over dx is equal to f of x and y, which is the most general form. And this is the first order ODE. The initial condition is y at x0 is y0, and we are also given the step subs. If you remember the general form of equation for extrapolation of yi plus 1 based on yi for the Runge-Kutta methods is equation number 1, which basically relates yi plus 1 to yi plus phi times h, and phi is some sort of a slope for the line that takes us from yi to yi plus 1. In the Heun's method, we kind of modified the Euler's method for estimating the slope of that line, and basically we chose the average of the slope of the curve at the beginning and at the end of interval, which is more accurate compared to the Euler's method, which is just based on the slope of the curve at the beginning of the interval. So for that, we calculated the slope of the curve at the beginning of the interval, which is easy. Basically, the tangential line is this blue line. The slope of the tangential line is f at xi and yi, and this is based on our equation, which defines the slope of the line is equal to f of x and y. At the end of the interval, we can follow the same procedure to estimate the slope of the function, and by slope of the function I mean the first derivative of the function or the slope of the tangential line to the function. But the problem is the slope of the function is f at xi plus 1, which is known, and yi plus 1, but we don't have yi plus 1 at this point. So what we do is we introduce an intermediate value for yi plus 1, and we show it with an asterisk, and this value of yi plus 1 is obtained using Euler's method. So basically this blue line, wherever it intersects with the vertical line that passes through xi plus 1, will be our yi plus 1 asterisk. Then we feed the value of yi plus 1 asterisk to f, and then we obtain the slope of the tangential line at the end of the interval. Then with the slope at the beginning of the interval, which is the slope of the blue line, fxi and yi, and the slope at the end of the interval, which is the slope of the red line, fxi plus 1 and yi plus 1 asterisk, we calculate the average of the two, which is this green fraction. And that basically defines a new line, or this green line, which gives us the value of yi plus 1 at the end of interval, and this is based on the Heun's method. And the true value is this pink point, and you can see using the Heun's method we can estimate the value of yi plus 1 more accurate. So the Heun's method uses this equation number 3, to calculate the value of yi plus 1. Now I just introduced another equation number 4, which is basically saying that x at the end of interval is x at the beginning of interval plus the step size. And then if I substitute equation 2 and 4 into equation 3, I will get a more general form of Heun's formula, which is, so if you notice, I replace yi plus 1 asterisk with its value from equation 2. Now I'm gonna name some of the terms in this equation, and I start with these two constants. So I'm gonna call them A1 and A2. And if you notice, A1 and A2 are the weights that we assign to the slopes of the function at the beginning and at the end of interval. And based on these weights, we can come up with a weighted value for the slope of the line that we want to use to extrapolate the value of the function at yi plus 1. The next terms are these two terms, and I'm gonna call them K1 and K2. And K1 and K2 are basically the slope of the function at the beginning and at the end of interval. And if you again notice, K2 includes K1. So I'm just gonna make sure that we are clear that this is the formula for Heun's method. And the reason that I just rearrange this formula is not for simplicity or anything like that. The only reason is I want to make sure that when I next introduce the general form of Runge-Kutta method, you can connect it with this formula and it helps you in understanding general form. Now with this I can start introducing the general form of Runge-Kutta method. Now imagine instead of using the slope of the function at the beginning and at the end of interval, we use the slope of the function at multiple points within the interval. So I just try to show it graphically in here. So in the similar fashion as we explained before, at each step of calculation, we have the value of the function at the beginning of the interval, which is yi, and we want to estimate the value of the function at the end of interval, which is y at xi plus 1 or yi plus 1, and the step size is h. So now if I want to calculate the slope of the function at some intermediate points, firstly I have to define these intermediate points. And let's say I just introduce them as xi plus a fraction of a step size. And for the fraction, I use p1 times h. Then I have another one, which is xi plus p2 times h, and so on and so forth. So what I'll do is I try to calculate the slope of the curve at these intermediate points. And again, it's in a similar fashion to Heun's method. First, we have to calculate the value of the function or estimate them. at these points, and then we have to use those values and put them into our function f to estimate the slope of the curve at these points, which are these lines. And let's say we calculate the slope of the curve at the beginning of the interval 2. And I'm gonna call this k1, next one k2, next one k3, and so on and so forth. So with this in mind, I can now write the general form of Runge-Kutta method, which again starts with our famous formula for yi plus 1. So just notice that in here phi is a function of xi, yi, and h, and can be written as, and if you noticed, phi in here is calculated based on slopes of the function at different points, which are k1, k2, all the way to kn, times some sort of weights, which are a1, a2, all the way to an. So phi is some sort of weighted slope for the function within the interval that we are solving. Next, I have to define the k's, which are, so the simplest is k1, which is the slope of the curve at the beginning of the interval, and then we have k2 all the way to kn, which are, so if I number these equations, this will be equation 6, 7, and this set of equations that gives us the values of k1 to kn, I'm just going to call it equation 8. So again, the reason I reiterated the Heun's method was to give you some understanding of what's happening in the general form of Runge-Kutta method. So if you compare it, we have some weights. For Heun's method, we have A1 and A2 only because we only use the slope at 2 points. But in general form, we have A1 to AN because we are using n points to calculate the slope. Then we had K1 and K2 in Heun's method. Here we have K1 to Kn, which are the slopes at different points. And the values of the slopes are calculated using our f function. So the simplest one is k1, which is f of xi and yi. The next point is xi plus p1 times h. So k2 is f of xi plus p1 times h. And the y at this point is estimated as yi plus q11, which is a constant, times k1 times h, which is again very similar to what we had in Heun's method. It was yi plus the constant in here was 1 times k1 times h. So with that, let me just summarize the constants in here. All a's, p's, and q's are constant, and k's are series of recurrence relationships. And by that I mean k1 appears in k2, k1 and k2 appear in k3, and so on and so forth. So equations number 6, 7, and 8 define the general form of Runge-Kutta method. And the values of the constants, a's, p's, and q's, can be obtained by writing the general form of Runge-Kutta method at certain order, for example, first order or second order or third order, and then writing the Taylor series expansion for the same order and comparing the two term by term. Just to clarify this, I first give you an example for the first order Runge-Kutta, which corresponds to n equal to 1. If I choose n equal to 1, then I will have, so I just substitute the value of k1 into phi and the value of phi into yi plus 1, and then it gives me yi plus 1 is equal to. Now what I'll do is I also use Taylor series expansion to estimate the value of yi plus 1. And because we are deriving the first order Runge-Kutta method, which only contains two terms, I'm gonna truncate the Taylor series expansion after two terms, and we know that the order of error in here will be h squared. So if we compare equation 1 and 2, we come up with some interesting results. Firstly, a1 is 1. And for the second conclusion, I remind you that we know that Runge-Kutta methods have some local truncation errors. So I just show it in here by local truncation error. So our second conclusion is that the local truncation error is of the order of h squared. And finally, I will just rewrite the equation. So if I use n equal to 1, the first order Runge-Kutta method will be yi plus 1 is equal to yi plus f of xi yi times h, and this is what we already studied as Euler's method. The next example will be a bit more complicated, but again that will help you to understand this general form of Runge-Kutta method, and for that I'll just do the same thing for n equal to 2. Substituting n with 2 in the general form of Runge-Kutta yields this system of equation. Now if I substitute k1 and k2 in phi and then substitute phi in the equation for yi plus 1, then I get the new equation for yi plus 1, which is and the unknowns of this equation are a1, a2, p1, and q11. Now compared to derivation of the first order Runge-Kutta method, there is one more step in here, and that's the expansion of this term using Taylor series. But before I start the expansion, I'll have to give you a refresher on Taylor series expansion for a function of two variables. Now let's assume that we have a function g which is a function of two variables, x and y. So using Taylor series expansion, we can estimate the value of this function at x plus r and y plus s based on value of function at x and y plus the partial derivative of the function with respect to x multiplied by the variation of x, which is x plus r minus x, plus the partial derivative of the function with respect to y multiplied by the variation of y, which is y plus s minus y. And I just remind you that there are other terms but I'm just gonna truncate it in here. So if I simplify this, it will be g of x and y plus r multiplied by del g del x plus s multiplied by del g del y. And of course, because we truncated the Taylor series, there will be an truncation error in here. Now, let's apply the same concept to this term. F at xi plus p1 times h and yi plus q11 times k1 times h. So I can write this as f of xi and yi plus the variation in x multiplied by derivative of f with respect to x plus the variation of y multiplied by the derivative of the function with respect to y plus the truncation error, which is of the order of h squared. Now, before I move forward, let me just number these equations in here. And then I put equation 2 into equation 1, which results in and now if I expand this, I will have and finally I will just factor some of the terms in here, and I rewrite yi plus 1 as and I'm gonna call this equation number 3. So from this point on, we will follow the same procedure that we used for the first order Runge-Kutta, and that's basically using Taylor series expansion to expand yi plus 1 based on yi. The only difference is here we will add one more term before the truncation. And if you notice, now that we use more terms in Taylor series expansion, f prime also appears in here, which is the first derivative of f and the second derivative of y. So I use the chain rule to expand f prime. And now I'm gonna number these two equations. And if I put equation number 5 into equation number 4, it results in so at this point we have two expressions or two equations for yi plus 1. One is equation number 3 and one is equation number 6. So if I compare these two equations term by term, I can see that they both have yi, which is the first term. Then in equation number 3, I have a1 plus a2 times f of xi and yi times h. And in equation number 6, I have f of xi and yi times h. So the first conclusion is a1 plus a2 is equal to 1. And then if I compare the third term, I can conclude that a2 times p1 is equal to 1 over 2 and a2 times q11 is equal to 1 over 2. And as you can see, both expressions have truncation errors on the order of h cubed. So this set of equations, if you look at it, we have 3 equations and 4 unknowns, which are a1, a2, P1 and Q11. So consequently, we will have unlimited possibilities for the solution of this system of equation. So the way we would go about solving this system of equation is we will take an arbitrary value for one of these variables, for example, let's say A2, and then with that we will have three equations and three unknowns, which makes it a well-defined system of equations, and we can obtain a specific solution for that. Now let's have a look at some of the common options for solving this system of equation. So our first choice is assuming A2 is equal to half. So if we replace that into the system of equation, we get A1 plus 1 over 2 is equal to 1, which results that A1 is equal to 1 over 2. 1 over 2 times P1 is equal to 1 over 2, which results that P1 is equal to 1, and 1 over 2 times Q11 is equal to 1 over 2, which results that Q11 is equal to 1. So now if we substitute these constants back into the general form of Runge-Kutta formula, we get yi plus 1 is equal to yi plus a1 times k1, and in here a1 is 1 over 2 times k1 plus a2 times k2, and here a2 is again 1 over 2 times k2 times h. And based on the definition, k1 is f of xi and yi, and k2 is equal to f of xi plus p1 times h and yi plus q11 times k1 times h. And because P1 is equal to 1 and Q11 is also equal to 1, I'm just going to delete them from here. So these three expressions together, they form the second order Runge-Kutta formula, assuming that A2 is equal to 1 over 2. And if we look at this more carefully, xi plus h is xi plus 1, and yi plus k1 times h is actually what we define as yi plus 1 asterisk in the Heun's method. So we can recognize that this is in fact the formula that we derived for the Heun's method. The next common solution for the system of equations that we obtain for the second order Runge-Kutta method is by assuming that A2 is equal to 1. Again, if I go back to the equation and put A2 is equal to 1, A1 becomes 0, P1 becomes 1 over 2, and Q11 becomes 1 over 2. So I will just write them down here. And again, by substituting these values for the constants in the general form of Runge-Kutta method, we will get yi plus 1 is equal to yi plus, we have a1 times k1, and in here a1 is 0, so that whole term is 0, plus a2 times k2, a2 is 1, so we will have k2 times h. And then we have to write k1 and k2. So k1 is again f of xi and yi, and k2 is f of xi plus p1, which is 1 over 2 times h, and yi plus Q11, which is 1 over 2 times K1 times H. And these three equations together form the second order Runge-Kutta formula, assuming that A2 is equal to 1. And again, if we look at this more carefully, we realize that xi plus h over 2 is what we call as xi plus 1 over 2, and yi plus 1 over 2 times k1 times h is what we call as yi plus 1 over 2 in the midpoint method. And indeed, these three equations together, they are equivalent to the midpoint method. Now we can conclude that for the second and higher order Runge-Kutta methods, there are multiple possibilities. And depending on how we solve the system of equations for the constant, we may get different formulas. I think at this point I can wrap up the derivation of equations. I believe I've given enough information for you to drive any order of Runge-Kutta method. You can try by yourself to drive the third order or fourth order Runge-Kutta, but it's not really the subject and the scope of the course. What I will give you next is I will go back to the slide and present you some common forms for the third order and fourth order Runge-Kutta method. Here I'm presenting the third order Runge-Kutta method by making n equal to 3. And as I mentioned, there are multiple possibilities depending on how you go about solving the system of equations for the constants. But this is one of the very common ones. And as you can see, we have the definition of yi plus 1 based on yi, k1, k2, and k3. And the order of the local truncation error is h to the power of 4. And these are the definitions of K1, K2, and K3. I have to mention that this is the way that your textbook, which is Numerical Methods for Engineers by Chapra, writes this system of equations for Runge-Kutta method. But if you refer to the other reference books, you may see that some books, they basically include H into the definition of K's. For example, you see there is an H in here, and here, and you don't see this H. But again, these are just the same thing presented in different forms. And in this slide, I also showed the fourth order Runge-Kutta method, which is obtained by making n equal to 4. As you can see, yi plus 1 is a function of yi, k1, k2, k3, and k4, and the local truncation error is on the order of h to the 5. And these are the definitions of different k's. I think at this point I can wrap up this session. Thank you very much for your time, and see you in the next lecture.